This is Catherine Schmer, and in this video we talk about symmetry tests for polar graphs. A graph is symmetric about the x-axis if it is a mirror image of itself over the x-axis. So for example, if we have the point r theta in quadrant 1, then we'd have to have the point r negative theta in quadrant 4. Or another way to list this is negative r pi minus theta, which would also be in quadrant 4. So that's our visual test, is whether or not the graph is a mirror image of itself over the x-axis. Now what if we wanted to test algebraically whether a function is symmetric about the x-axis? Well, if we have the function r equals f of theta, so in other words r is some function of theta, then r is symmetric about the x-axis if f of negative theta equals r. That's what this first point in the image is saying, r negative theta, or f of pi minus theta equals negative r, and that's what this second point is saying, negative r pi minus theta. So you can use either one of those to test, and depending on your function, one way may be easier than the other for proving that it's symmetric about the x-axis. But you definitely want to do the visual check first. If it doesn't look like a mirror image over the x-axis, then you can automatically say, well, it's not going to be symmetric about the x-axis. But if it does look like a mirror image of itself over the x-axis, then you can perform this algebraic test to prove it. Now, a graph is symmetric about the y-axis if it's a mirror image of itself across the y-axis. So if I have the point r theta in quadrant 1, then I would have to have the point negative r negative theta in quadrant 2, or another way to write this would be r pi minus theta in quadrant 2. Now algebraically, if r equals f of theta, and we want to show that the graph is symmetric over the y-axis, then r is symmetric about the y-axis if f of negative theta equals negative r, and that's what that point negative r negative theta is telling us, or f of pi minus theta equals r, and that's what that second point r pi minus theta is telling us. Now there's one more symmetry to think about, and that is symmetry about the origin. And the way that works is, the way I think about it is if I flipped the graph over the x-axis first and then the y-axis, then I would need to end up with the same graph that I started with. The symmetry about the origin can be a little harder to visualize, but the algebraic formula is that if you have the point r theta in quadrant 1, then the point negative r theta would be in quadrant 3, or that's the same as saying r theta plus pi in quadrant 3. So if r equals f of theta, then r is symmetric about the origin if f of theta plus pi equals r. So that will be our algebraic test for symmetry about the origin. Now let's use an example that we created in the last video, the graph of r equals 6 sine of 2 theta. So we already graphed this in a previous lesson, and we ended up with this 4-leaved rows, and it has each leaf is centered in its own quadrant. We have one leaf in each quadrant, with the tip of the leaf being at the angle pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. So first question, is the curve symmetric about the x-axis? So let's look at it. It looks like if I take the top half of the rows, the first quadrant leaf and the second quadrant leaf, and flip them over the x-axis, then I would get the mirror image. So it looks like the graph is a mirror image of itself over the x-axis, and so I would say yes, it is symmetric about the x-axis. Now to prove that, I'm going to use the formula and show that f of pi minus theta equals negative r. So if you recall, that's one way to show that a graph is symmetric about the x-axis. So f of pi minus theta equals 6 sine of parentheses 2 parentheses pi minus theta, close all the parentheses. So I'm just plugging in the pi minus theta in the place of theta. So this is equal to 6 sine of 2 pi minus 2 theta. Now I can get rid of the 2 pi, so this is equal to 6 sine of negative 2 theta, and the reason for that is because 2 pi is a full period for sine. So sine of 2 pi minus 2 theta is equivalent to sine of negative 2 theta. And sine is an odd function, so I can pull the negative out front. So this is equal to negative 6 sine of 2 theta, since sine is an odd function. And notice that's just negative r, which is what I was trying to prove. So we've algebraically proved that r equals 6 sine of 2 theta is symmetric about the x-axis. Now let's do the y-axis. So is the curve symmetric about the y-axis? Well, if I look at the right half of the graph and the left half of the graph, they're a mirror image across the y-axis. So I would say yes. And to prove it, I want to show that f of negative theta equals negative r. So I plug in negative theta. F of negative theta equals 6 sine of 2 negative theta, which is equivalent to 6 sine of negative 2 theta. And since sine is an odd function, I can pull out the negative. So that's negative 6 sine of 2 theta, which is negative r. So we've proved that it's symmetric about the y-axis. One more left. Is the curve symmetric about the origin? Well, if I flipped over the x-axis and again over the y-axis, I would end up with my original curve. So that's how I think about symmetry about the origin. So I would say yes in this case. And to prove it, I want to show that f of theta plus pi equals r. So f of theta plus pi equals 6 sine of parentheses 2 parentheses theta plus pi, close all the parentheses. Distribute the 2, so that's equivalent to 6 sine of 2 theta plus 2 pi. And since 2 pi is a full period of sine, this is equivalent to 6 sine of 2 theta, which is r. So we've proved that our graph is symmetric about the x-axis, the y-axis, and the origin. The reason we care about symmetries in polar coordinates is because in the next section, when we start doing areas inside of polar curves, sometimes it's a lot easier to set your bounds if you know that you can just find a little piece of the region and then multiply by 2 or multiply by 4 because of a symmetry. For example, if I wanted to find the area inside all of the leaves of this rose, I could just find the area inside of one leaf and then multiply by 4, or maybe the area inside of half a leaf and then multiply by 8. So it can save me some calculations if I recognize the symmetries.